All right. So moving on to the next part, we already defined that R has to be less than 1/2 in order for the simulation to be stable. So now we're going to use the Crank-Nicholson equation. So basically, it would look like delta t del t equals alpha delta squared del x squared. And then what we did with this was we had del t equals alpha. It was basically just our two differentials of temperature with respect to position, change in x. But what we can do with the Crank-Nicholson equation or Crank-Nicholson method is we can do the same thing, but we can lose a tiny bit of accuracy. Or actually, I don't know if it's tiny or not. I just know that this is valid. If we take the average of the same thing, but we're also going to include this at, what was this? So this would be at a different time step, which would be 1 time step forward. This one minus this same thing up here. Minus that. So basically, we repeat all of this, but at the next time step, and just divide everything by 2 to get an average. And we'll see why we're going to do that in a minute. So we'll go ahead and write out what we had. So it was t n plus 1 at the position we're looking at, minus t in j, changing time, equals alpha over 2 t plus 1 j plus 1 minus t j n plus 1 2 plus t j minus 1 n plus 1. Oh wait, sorry, we're doing an average, it would be plus. This squared t, and then this is all at the current point in time. 2t t j minus 1 n. So this is basically what we're doing with the Crank-Nicholson equation. We'll go ahead and pull out our x squared 2 out here, and then move t over here. Plus 1 j minus t j n equals alpha times delta t over 2 delta x squared. And we're going to say that all of this again is r. So it looks just like our previous r, but now it's divided by 2. Yeah, all that basically j plus 1 n plus 1 minus 2 t j t j minus 1 n plus 1 plus t j plus 1 n minus 2 t j n plus t n j minus 1. Okay, so from here we basically do the same thing. Oh shoot, this isn't up high enough. we do the same thing. This is recording. Okay, we're good. Same thing where we set t equal to t of n, j is equal to e negative alpha k squared. Is this time? Yeah, time. Or accurately, n delta t times e I k j delta x. So then that means that something like, let's do tn plus 1 j plus 1 equals e k2 n delta t e I k j delta x times e alpha k squared delta t e I k delta x. So it's the same thing, but just an additional, or like this would be like j plus 1 times delta x, or n plus 1 times delta t. So in this, you're giving both a position step and time step for the temperature that we're looking at compared to what was originally there. Is that? No, that's not super legible on their end. So then t n plus 1 j plus 1 equals t j n times e alpha k squared delta t e I k delta x. Okay, so we take this basically principle, and we want to separate all of our n plus 1 terms to one side and just n terms to one side. So what we'll do is this straight, there we go. Straighten this out. Okay, so we have t n plus 1 j minus r times t n plus 1 j plus 1 minus 2 t n plus 1 j plus t n plus 1 j minus 1. That equals t n j r, and that's the exact same thing, but the previous or the current time step. So t j plus 1 n minus 2 t n j plus t n j minus 1. So now we want to incorporate our equation for each temperature into here, and we want to separate t, j, n plus 1, and t and j all by itself. So this would then turn into n plus 1 j minus r. This would be t n plus 1 j times, extra time step would be e. No, an extra position step would be e I k delta x minus t, no, 2. Let's make this smaller, we're running out of room. minus 2tn plus 1j plus tjn plus 1 times e to the negative ik delta x. N plus r, and we're going to do the same thing to the side. So it would be t j times e ik delta x minus 2 t j n plus t n j times e negative ik delta x. Okay, so we just take this in the same direction that we did the other one, where we transform these e raised to I components, and we turn them into a cosine function. N plus 1, 1 minus r e I k minus 2 plus e negative ik delta x equals t j n plus tjn. Factor that out. 1 plus r t, no, t's are out. E I k delta x minus 2 plus e negative I k delta x. Okay, so both of these should look, so both sides should look almost identical, except the side that has the next time step is going to subtract 1 from, or is going to have 1 subtract from all this, and then the current time step is going to have this added to 1. So we'll isolate our temperature at our current position at the next time step. That equals our time step plus r. And now we're going to convert this to our cosine function. So e raised to I times some kind of variable plus e raised to the negative I times the same variable equals cosine of that variable. Or it would equal to cosine of that variable. And that variable is k delta x minus 2 over 1 minus... Did I switch signs up? I did. Let me go back to this. Where did I mess up? I'm pretty sure the negative part needs to be on top. Let's go ahead and just write it out. R2 cosine k delta x minus 2. Yeah, that's not correct. The negative part needs to be on top. I either messed up in the algebra somewhere or I messed up deriving the equation. Okay, I'm gonna check where I messed up and then we'll come back to this. Okay, we were on the right track. I was just not thinking smart enough. There we go. Basically, this is correct. We need to switch the sign in the parentheses. So we need to turn this into 1 minus cosine of what's in the brackets. So it would be, so you would subtract this term instead. So 2r 1 minus cosine what's in the brackets. Or 1 plus 2r 1 minus cosine what's in the brackets. Okay, so the entire reason of why we did Crank-Nicholson was so we could have this right over this. But if you look at this equation, 1 minus cosine of x will either always be positive or it'll be either be positive or it'll be 0. Which means what will eventually happen is this term on the top will always be smaller than this term because you have all of this plus 1 and then you have all of this being subtracted from 1. So no matter what value you use for r, everything that's on the top is always going to be smaller than everything that's on the bottom, meaning that your temperature at a later point in time will never go to infinity, and it's never going to be larger than your temperature at your current time. So you can use any value that you want for R. All right, so now on to the final part of Part C. So they want us to discretize the bar with 20 time-dependent temperatures and solve the equations from Part C using this in Python. But let's actually get to the part where we let's show how we're supposed to use the matrices and linear algebra to actually solve for this. So to do that, we're going to go back to let me double check and make sure this is recording. Yep. All right. So we're going to look back at this right here. Before we kind of converted everything to a cosine function. So we're going to look at this and we're going to go ahead and factor that r out. So we'll have, we might have to go onto a different page for this, tn plus 1. So we're looking on the left side, we have all the stuff at a later time period, minus t j plus 1 n plus 1 is 2t n plus 1 j is t j minus 1 equals t n j plus r t j plus n, no, plus 1 n is 2 j plus t j minus 1. And then these are all of our spots at time, at our present time. So what we want to do is we kind of want to organize everything in terms of our temperature variables. So we'll kind of factor out everything that's out in front. So we'll have negative R Tj plus 1. And we'll go from forward position to backward position. And then it would be plus... Oh, shoot, we forgot to factor out that R. R and R. So the R's were in there. 1 minus 2R Tj plus 1 plus R Tn plus 1 J minus 1. Let me double check and make sure that looks correct. Okay. And then same thing on this side. R T N J plus 1 plus 1 minus 2R T J N plus T N J minus 1. Okay, so yeah, everything should look the same except this term has a negative out in front and this term's positive right here. So let me get a fresh sheet of paper so we can, sorry, this is stuff from way later in class, so we can actually write out the bar. So I'm just going to write this out in 2D because that's a lot easier. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, that's not, we're not going to be able to get 20, but that's okay. So we have T naught out here up to Tn positions. And let's write out what we had. I'll probably have to flip back to check on it. N plus 1, J plus 1, plus 1 minus 2R, T. Let me write the R in front, that's easier. J plus T N J. All right. So here's what we have going on. We have 20 different T's that we need to figure. So we're going to start out by trying to find all of our T's at the next position in time, or the next point in time. But we got 20 of them. So what we can do is we can actually set this up as a matrices. And if you do that, then you would have all of your T's. So this would be a single column. And then you would multiply it out by its coefficients. And then we have 1 minus 2R. And then the next spot we have R. And if you multiply all that out, then you would get this going down in this column to the left. And well, if you have that, if you get this equation, then that's just equal to this. So you can substitute this in for there. So you would have this on the left. So basically what would happen is you would have 20 unknowns, but you would also have 20 equations. So if you do a matrix multiplication, then you can work backwards and actually solve for all of the t's that you need. So it would start at t and not, and then we would get back down to tn. These are going to be constant. They're always going to be, I think, 40 and 80. So luckily you get to know these. Then you would have t n plus 1. So that would be 1. T2, T3, T4, T5, and so on. T9, T10. I mean, I guess just pretend that this goes all the way from T10 down to T20. And then when you matrix multiply, that should give you all this. And since you know your temperatures at the current point in time, you're able to solve it and figure out what they would be at the next point in time. So we're going to actually matrix multiply this out. I'm going to pause the video here and then rewrite this just so it's a little bit neater, but it'll be the same thing, but just neater. So back to this, we see everything clearly. Oh gosh. Okay. Also, I misspoke. The lower subscript, those are, it was supposed to be, I wrote this, it was supposed to be, what did I write the first one? Oh, here we go. It's not supposed to be upper subscript. Sorry, it's supposed to be lower subscript, so you're solving for different positions. But like I said, when you substitute in that equation, you can find it for the later time period. So when you solve all of these are just going to be in a certain position, but at the next time step. So let's go back to this. I rewrote our bar, and I did, I'm just going to do 6 for sake of, or no, it would be 7 discretizations for sake of this example, just so it looks nice. Okay. So, and I forgot to write out the equation. T n plus 1, j plus 1, is 2r. Oh, t j n plus 1 r t j n plus 1 equals r t j n plus 1 minus 2r t n j plus r t j n minus 1 plus 1. Minus 1. All right. So now we can really get started on this. So like I said, basically what we're trying to find is you're trying to find what all of these values are. So you kind of start at the end and work your way backwards. So let's start out with this spot right here, and we'll explain why in a minute. So we're going to look at the temperatures at position 2 on our bar. So we have, we'll write out the right side. So that's going to be, and this is just a vector of, oh gosh, 1 by 6. I need to, or no, 1 by 5. I need to get the nomenclature down. 1 minus 2r tj n plus rtj minus 1 n. Okay. So when if we want to get that, then we would basically just on this side we would have negative r, because it would be this right hand side. 1 minus 2r 0. I think it would just be 2 spots left. Okay. So basically in a matrix when you're multiplying matrices, you're going to take these guys and kind of flip them over top like that. So it would be T1, T2, T3, T4, and T5. So let me kind of split this up. So this is useful because when you matrix multiply, you're going to be left with this, and then if the rest of these are just zeros, then you don't have to worry about T4 or T5. So if you go to the next row and if you decide to look at T3, then you would have negative, or actually, let's do this. Also, I didn't write down the numbers. 3, 2, and 1. So then if we look at 3, then we're going to have RT4 plus 1 minus 2R T3 plus RT2N. These are in. So how we get that? We do the same exact thing. Minus 2R, R, 0 right here. So we don't have to worry about T1 or T5. So basically what we have going on here, and we're going to keep doing this same pattern, is we have a tridiagonal matrices where you only, you can have diagonal, tridiagonal, diagonal, but basically you have, in this case, we would have 3 sets of constants. So we have negative R, 1 minus 2R, and R. And instead of going in a single direction or in a single direction sideways or a single direction downwards, we're having it go straight down the diagonal. So that's why it's called tridiagonal. And when you do that, everything else is just filled in with zeros because you still have to have it in a rectangular area. So when we do that, matrix multiplication turns out nice. We get 5 on this side plus 2R T4N plus RTN3. And then same thing down here. We would get, we would get 1 minus 2R T5N plus. Okay, and then when we do this one, we have 1 minus 2R up here, R 0, 0, 0. So we have 1 minus 2R T1 T2 N. So we're missing. So when you look at, when we do the multiplication for the first one and the last one, we're missing the front term on the last one and the back term on the first one. And basically how you make up for that is when you have the equation on this side, you can just do T naught minus R. T naught times negative R. And if you are subtracting it from this end, then that's just the same as multiplying it on this end. So then that matches our equation. And if they were unknowns, then we would not be able to do that. But since the temperatures are always constant on the ends, I think it's 40 and 80, that does in fact make it possible. So then we would have the same deal on this side. We would have STN R, then you just add it over here. Or no, it would be negative. But since we're substituting the equations in, it would end up being positive over here. in. So that's basically all that we have going on over here. Again, just to reiterate, we have all of our constants in this matrices, but it's going in a diagonal direction instead of a single sideways or downwards direction. And we'll show what's going on we'll show how to code that into Python whenever we get to that step. And then we have the equation of all of our known temperatures at the initial point in time. And then whenever you divide this matrices, or when this matrices is divided by this matrices, then you're going to be able to solve for all of these values. And we'll get into that on the Python portion. All right. So I did mess up on the derivation part back there. These are the so these are time or temperature values at the next time step, and then these are our current ones. Back there, I accidentally wrote for both sides that it was 1 minus 2r just because I messed up on the algebra. On the left side, it's actually supposed to be 1 plus 2r, and this r is negative right here, and then this r is positive. We got that part right. We just messed up right here. That doesn't really change anything. It would only screw us up if we coded that into our Python script, but everything else should be the same. I mean, the principle with the tri-diagonal matrices and solving for our next temperature values is still the same. So let's actually get down to the coding part. So we're going to set our temperature values for our right side and our left side. So right is going to be our 80-degree one. And our left side is going to be 40 degrees. We need our actual bar. So that's going to be np.full. Oh, and we want 20 discretizations. I want 20 of these, and we all want the values to be 20. Okay, so and then we actually need to start writing out the code for that. The code for the tri-diagonal matrices. So that's going to be, we're going to have our diagonals. It's going to be 3 of them. That's going to be np.vstack. So this is what lets us actually use diagonal matrices. I think there's an underscore. Okay, so, oh gosh. So the top one is going to be notated with the 0 out in front. And then I think it's np.full. We need 19 of these because our diagonal would be 20. Our middle one would be 20. The top and the bottom one are going to be 19. So it would be n minus 1. And then it would and the next one would just be np.full. And this is going to be n, and then the constant that we would have in that spot would be 1 plus 2 times r. So basically this negative r is just this guy right here. The 2r plus 1 is going to be this, and then we need r for the last one. So that's going to be np.full n minus 1 again, so we need 19 spots. And then it's r, and then for it to be the lower one, it's going to be 0 on the bottom. I know that we're definitely missing something. the idea is right, but our syntax is definitely wrong. So we're going to run this and we're going to see what is going on with that. So we will be right back, guys. All right. So I figured out what was going on with this one. First, there's not supposed to be an underscore. And these are supposed to be np.r. No, this one's full. These are np.r. Comma 0 is out here. 0, comma. This one's dot r. Takes 3 were given. Oh. Okay, let me move on to the next part. I know that we'll need to come back to this anyway. Okay, where did we start? I need array of all of the values that we obtain. It's going to be t. So that's going to going to start with our initial ones. I initially labeled this as t temps. And technically, I guess since we hadn't made any progress with the bar, it would be all of our temps. But now we're going to notate that as our initial values. So t initials. Our old values. So we're going to need to keep track of those, and that's just going to be t initial. I need a copy of that because we don't want to change those. And then I think it said that we want to run the loop for I think 100 times for I in range 100. So we'll go ahead and say what our current we'll just define what our current is. So that would be R times, oh shoot, we need to define what our t temps are. That would be t temps. We have up here. It would just be t left. T left. That would be t temps plus 1 minus. We never stated what r was. R is going to be 2 because, again, we're trying to prove that we can successfully do this with the Crank-Nicholson equation when r is a value greater than 0.5. So minus 2 times r t temps. Okay, and we want this to be our next value, so we need 2. And then t temps, and then the one in between, so -1 and 1. And then finally r times t times and then we need to again state that. So our first one is just going to be t left -1. Okay, let me figure out what was going on with these, and then we'll come back to this. All right, so this is the end of process dynamics homework 2, part C. We actually had all the code that finished this, and then we lost the last part of the video, so we had to go back and delete the code that we had up until this point. But we left off with the issue of this is supposed to be -1. And then this should be called t next. So then t history, oh gosh, history dot append t next, and then t old equals t. I apologize for auto-generate. I legitimately do not know how to turn that off. Right, so then t equals np dot array. Should it be dot full t history? No. T left t history, and then t dot vstack t history dot full t right t history. Yeah. So get rid of our error. We might have to run everything. Yeah, we need to run everything. Cast with shapes. Oh, goodness gracious. Thought we just fixed this. All right, we'll be right back. All right. I think I overcorrect. Yeah, I overcorrected from the first time because it's supposed to be 1 to -1. Because I was thinking of having these go in numerical order from left to right, but it's supposed to be second from the first value and then second from the last value. That's the order that it's supposed to go into. And then we had these need to be switched. And then this needs to be the UN of history. Same thing for the right side. We were given. Okay. Right. This was not working because we had the entirely wrong operator. It's supposed to be mp.c. All right. So now we can plot this. So our x values are going to be p dot range, t dot shape 1, fig 2 equals make subplots. Again, I apologize for the auto-generated. The t-shape 0. Okay. So it should be all of these, but we need if we only want it in discretizations of 10. We don't want to make a bunch of these. Oh, wait. Okay, the operator is, okay, %10. Oh, wait. So if the remainder divided by 10 equals 0, there we go. There's no arrange. Someday I'll get it right. We need our fig 2. Here we go. We use our Crank-Nicholson equation to show that even when we have a value of r that's greater than 0.5, we don't get these crazy oscillations. So that should wrap up homework 3 Part C.